Well, hello there, chemistry students. We're doing lesson 10.2, where we're going to take a look at gases and pressure. In this lesson, we want to describe the relationship between temperature and energy of molecular motion. We want to show you the importance of looking at the Kelvin temperature when you're relating temperature to kinetic energy of molecules. We're going to define pressure and explain how gases exert pressure, as well as recognize several of the units that we use to measure pressure, and we'll do a little bit of practice with reading pressure devices such as barometers and manometers. Alright, let's get to it. Introducing alright.
Alright, so we're going to talk about the temperature and kinetic energy of molecules. In physics, back in your 9th grade year, we learned that kinetic energy was equal to 1/2 the mass times the square of the velocity. But in chemistry, we can also take that a step further and use another equation that is 3/2 R, which is a gas constant, times T. This allows you to see and relate velocity of the particles to the temperature of the particles. So if you see that, if we increase velocity, you would expect temperature also to increase. And of course, if we decreased velocity, then of course the temperature itself would also change.
So the upshot of all that is the temperature affects the velocity of molecules, and in turn then that affects the kinetic energy of the molecules, which is the fundamental assumption of our kinetic theory.
Yep. So if we increase the temperature, it increases the particle velocity. If we decrease the temperature, it decreases particle velocity. All good information that you have to know. And then lastly, we have to talk about the actual temperature that we're going to use for this. We use an absolute scale known as Kelvin. Now, what do we mean by absolute? Well, that means absolute zero, a term we used back probably in Unit 1 or 2, is 0 Kelvin. There is no temperature lower than that. And once we hit that, there is no kinetic energy in the particles, meaning they don't move. They're stuck in place, they don't vibrate, they don't do anything. And the reason we use this is for a good reason in the next lesson, because, well, we have to have a zero. We cannot have negative temperatures. So,
okay. And just so you know, when you see T in an equation in chemistry,
always assume Kelvin.
That is always, it needs to be in the Kelvin temperature, and we'll review again how to switch back and forth between Celsius, which is what we would normally be using in Kelvin. It's easy. But we need to have those temperatures in Kelvin for any calculations we do related to particle movement, energy, etc. Okay, let's move on. So one of the things that gases do that solids don't do and liquids don't do exactly the same way is exert pressure. Mm-hmm. Gases exert pressure against their container in all directions. What is pressure? Pressure's physical definition is written there, Mr. Hunter.
It's a force per unit area. And of course, the equation is just P equals F divided by A. It's a very simple and straightforward equation. We might use it once or twice as example problems or something. But
we have a little video to demonstrate this concept to us. So let's bring this up here. Okay, and I'll play it and we'll let you watch it.
So this is a unsharpened pencil.
Whacking it with a set of wrench or crescent wrench.
And there's a sharpened pencil.
Whacking it with the same force with a crescent wrench.
And you can see it punctured the cup.
So what the difference is, we had a difference in pressure. The pointy pencil had a much smaller area.
We had a very similar force. We can't say it was the exact same, but we had a very similar force.
I tried to hit it with the same force.
But the area decreased, which means the pressure, if we decrease the area, you increase the pressure of something drastically. So that's what that video is showing. Common units of pressure.
And this is for, by the way, gas pressure. You could use it for other things,
for liquid pressure
mainly
as well.
used for gases.
But we have kilopascals, which is kPa. We have atmospheres, ATM, torr, and millimeters of mercury, which are the same unit, basically. And then the American standard is PSI. We will not use PSI very often.
No, that's not really a standard chemistry unit, but it's
No.
used for tire pressures and whatnot.
And then, of course, we gave you a large conversion factor at the bottom here. This way we can convert between them using stoichiometry. We know 760 torr is equal to 760 millimeters of mercury. Like I said, they're the same unit, basically, which equals 101.3 kPa, which equals 1 atmosphere. Like I said, we're not going to use PSI. I believe Mr. Ferguson thinks it is 14.7 PSI per atmosphere. I'm not sure on that, but
It's close to that.
close enough. And of course, that all equals the standard pressure at sea level on a nice, clear day.
So the average pressure at sea level is equal to any one of these, depending on which unit you wish to measure. That's the average atmospheric pressure,
And you
the
can
pressure that
use-
gases in the atmosphere push on things.
You
with.
pretty much use any one of these to calculate pressures for gases, but we'll talk about that next lesson. Pictured below here is how gases exert pressure on their surroundings. They do this through collisions of their particles with the surfaces, or with whatever they're around. For example, humans have billions of collisions per second with their skin.
Gas molecules in the atmosphere striking our skin.
So, I mean, we have a lot of pressure on our bodies. Boxes.
About 14.7 pounds on every square inch.
Yep. And, you know, this is just how they exert pressure. You have billions of collisions.
Every one of these little collisions, you see there's a little red arrow pointing outward. So if you confine a gas into a container, its particles strike the surface, that's what creates the pressure.
And
So anything that increases the number of collisions or the energy of the collisions, as we're going to see, is going to increase the pressure.
Yep.
Anything that decreases the number of collisions or their energy will decrease the
we
pressure.
have a nice little demo to show you on that whenever we get to it, of course, in class. In the meantime, let's go look at the next thing.
So Mr. Hunter is unable to be with us for the conclusion of this video, but I want to end by showing you two important math skills that we're going to need as we get started with our gas law unit. And the first is measuring gas pressure. So there are two instruments used in a chemistry situation to measure gas pressure, classical instruments anyhow. Now today we have probes and things that we can plug into computers and some other various devices to use. But the first classical device was the original pressure measuring device. That's called the barometer. It was invented way back in the 1600s by the Italian Mr. Torricelli, who basically suspended a column of mercury, that's this black liquid you see here in the diagram, so that it was inverted, this column of mercury, in a tub of mercury, and the tub was open to the atmosphere. So those red arrows pushing down represent the atmospheric pressure pushing down on the mercury. And of course, mercury is a very dense, heavy liquid, and the mercury actually drops down, leaving a vacuum. This is an empty space with no air molecules in it, and the height at which the mercury settles would be a measure of the air pressure that's pushing down. And what Torricelli realized is that height changes from day to day. Some days the column was a little higher, some days it's a little slower, and he of course correctly explained that it's the weight of the air, or the force of the air pushing down, that's creating that height. So the harder the air pushes, the further up the column the liquid rises. So this number that I have here, 760 millimeters, if you measured the height from the surface of the mercury to the top of the column, the average air pressure at sea level on Earth is 760 millimeters of mercury. Now, in honor of Torricelli, that unit of millimeters mercury is also sometimes referred to as torr, T-O-R-R. So 760 millimeters of mercury, or 760 torr, would be one measure of average air pressure at sea level. So that's useful. That's a useful device, and we still have numerous other instruments that work in different ways, but that can be used to record the daily air pressure. What if you want to record the pressure of gas, say, in an enclosed system? We'll cover that in the next slide. How we would measure pressure in some kind of a sealed system or container is with a device called a manometer, And a manometer is used to another way of measuring gas pressure in a sealed container. It's basically a U-shaped glass tube. So this would be the business end of the manometer, and it's partially filled with mercury. So that grayish stuff we see in these is mercury. And they can be open, like the ones over here on the right that I'll look at in a minute. There's an open end to the tube that's open to the atmosphere, or they can be closed, like the first example that I'm going to show you right now. So let's take a look at a closed manometer. So you can, the manometer can be equipped or fitted to some kind of gaseous system like we see here, and will allow the gas to exert pressure, push against the mercury in the tube. And so basically how high it pushes the mercury in the tube, this delta H means height change, height difference, that's equivalent to pressure. So, and you can see we have a delta H of 50 millimeters of mercury, so the difference between this height and this height is 50 millimeters. That means the pressure can be 50 millimeters of mercury in that. So that's a closed-end manometer. Now the other kind is obviously the open manometer. So let's take a look at one of those. So here's one. The open manometer requires you to take an atmospheric pressure reading to really use it. So let's assume that the atmospheric pressure today is 760 millimeters of mercury. And what we see is the height of mercury on the open end exactly matches the height of the mercury that's being pressed on by this gas in the enclosed container. So there's 0 delta H. That means the atmospheric pressure is exactly equal to the pressure of the gas. This would be the gas, this would be the atmosphere. They're both pushing equally hard on the mercury, so there's no height difference. So that's how you would use a closed-end manometer. Now let's look at a second example here. Okay, so here's open manometer B, and in this case, we can see that there is a 50 millimeter height difference, and that the mercury is actually higher on the side towards the gas, and it's lower here on the side that's open to the atmosphere. So how do we interpret that? Well, it means the atmosphere is pushing harder than the gas. So the pressure of the atmosphere is greater than the pressure of the gas. So how do we find the pressure of the gas? Well, we simply take the greater value and subtract off the height difference. Okay, we're going to take the atmospheric pressure minus the height difference of 50 millimeters. And today the atmospheric pressure is 760. So 760 minus 50 would mean that the gas pressure is 710. All right, let's look at a third example. All right, so here's the opposite situation. So again, the atmospheric pressure is 760. But now we see we have a height difference of 50 millimeters the other way. The gas in the enclosed container is pushing harder than the gas in the atmosphere, which means this is the greater pressure. The pressure of the gas is greater. So what we need to do is take the atmospheric pressure and add on the height difference. So that's 760 plus 50. That adds up to 810. So the pressure of the gas in the container is 810. And we will practice this in class. It's just adding and subtracting, but sometimes it takes a little bit to wrap your brain around what you're seeing. So we'll continue to practice that. Let's go on to the last two slides. So to end this video, what we're going to do is take a look at some sample manometer problems, and then on the last slide we'll look at some temperature conversions between Celsius and Kelvin. So you might be faced with a problem like what we're seeing here, a manometer problem, and you're generally going to be asked to find the pressure of the gas that's in this enclosed container. So remember, it's going to be related to the height of the mercury column, or the height difference in the mercury column, and the atmospheric pressure. Okay, so you're always taking that height and you're either going to add it to the atmospheric pressure, or you're going to subtract it. And that, to me, is the most difficult thing to decide. So here's what we want to decide. Which is going to be greater, the pressure of the gas here or the atmospheric pressure here? Okay, look at the mercury column. Which gas is pushing harder, just looking at the picture? And hopefully you're seeing that this gas is pushing down and making the mercury move down further and pushing up the weight of the mercury here. So this gas is kind of winning the pushing contest, which means we want to kind of put a greater than. So the pressure of the gas in the enclosed space is greater than the atmospheric pressure. So that simply means we're going to take the atmospheric pressure, 755 millimeters, and we need to add the height, which is 24 millimeters, and that means 755, that's 779 millimeters of pressure. So looking at the problem on the right, we have a different atmospheric pressure, 763 millimeters, and again, that would have to be measured on the day that you were making the observation. And this time you notice that something a little different about the mercury column here. It's lower on the side that's open to the atmosphere and higher over here, which means the atmosphere is pushing harder now than the gas in the enclosed container. So that means the atmospheric pressure is greater than, so I'm going to put the symbol this way, the atmospheric pressure is bigger than the pressure of the gas. So if we want to find the pressure of the gas, now we're going to start with the atmospheric pressure of 763 millimeters, and we need to subtract off the 35 millimeters. So the atmospheric pressure, the gaseous pressure here is going to be 728 millimeters for the gas in the enclosed container. And we'll work some more of these examples in class. Okay, a final skill that we want to introduce in this video that you're going to be using repeatedly throughout the rest of the unit is that of temperature conversion. And specifically, we want to convert between the temperatures in degrees Celsius, which is typically what we would measure in chemistry, and the Kelvin or absolute scale of temperature. So on the right there, we've got a graphic, and Mr. Hunter, would you like to explain the kind of relationship between a Celsius thermometer and a Kelvin thermometer?
So how these temperatures were gotten. The Celsius scale, they took the freezing point of water to be 0, and then the boiling point of water to be 100. And of course, after that, we discovered something known as absolute zero, or we derived absolute zero, I should say. And then we had that derived as negative 273 degrees Celsius. So in these equations that we're going to deal with later in this unit, you can't have a negative temperature because negatives would cause other things to turn negative. So on the right here, they have the absolute scale known as the Kelvin scale. You can see the difference between 0 degrees Celsius and the freezing point of water for the Kelvin is 273. So this is a very easy relationship to solve for. Kelvin, to convert between Kelvin and Celsius, Kelvin just equals the degrees Celsius plus 273.15. And that's the...
Which for most purposes, 273 is okay, but technically it is 273.1.
And this is the easiest temperature to convert between. We also have Celsius to Fahrenheit, but we're probably going to give you that one if we ever have you use it.
The increments are the same. Like 1 degree Celsius is equivalent to 1 Kelvin.
And to show that even better, you can see here the difference between the freezing points is 273. And if you go up to the 100 degrees Celsius and the Kelvin point, it is 273 difference. So they have the same number of points between them. Between this point and this point is 100 degrees difference. Between this point and this point is 100 degree difference. And with Fahrenheit, that's not the case.
Right. Fahrenheit degrees are different sizes. But one other small point, but it is one that's kind of important. In Celsius, we call the unit a degree Celsius. So we put this little degree symbol up there. And in Kelvin, there's no degrees. Kelvin is just Kelvin.
Yep.
So whereas 1 degree Celsius, it's 1 Kelvin.
Yep. All right. I think we're done with you finally.
All right.
Have a good night.
Okay, so we finished the lesson on pressure. Now let's take a look at 3 post-video questions. Question 1, why do we have to use the Kelvin scale when we do math with temperature measurements? What's the importance of going with Kelvin? And then questions 2 and 3 both go with this diagram. So the first one's a general question. How does the pressure here relate to the atmospheric pressure? And then the follow-up question, if we know that the atmospheric pressure is 760 torr, so we have 760 torr here, what's the pressure in this container? So see what you can do with those, and we will go over them in class.